I'm Richard Doherty with the Envisioneering Group, and I'd like to be short in my introductions to Martin Kienzle, who I've known more than a decade. You know that his topic is on cognitive IoT, and cognitive, of course, was the theme of IBM. IBM CEO Ginny Rometty gave a keynote here on Wednesday. So, I'm sorry, on Tuesday. And while Martin works for IBM Research, he has enjoyed incredibly rich customer contacts with different industries, especially consumer electronics, home appliances, industrial IoT as well. And before IoT was called IoT, he and his associates were working in this area. He has a liaison with most of the IBM divisions, which only research people can do, is to peek over the fence and see if the terminology is correct, to see if they're on the same page about things. And that's why IoT is about to be continually supercharged through the cognitive services that Watson and other divisions are offering at IBM. He's been a contributor to standards back many, many decades that have been the topics of papers here. He is an IEEE Senior Life member, and he is a man ahead of our time. Please welcome me in welcoming Dr. Martin Kienzle.
Thanks, Rick. Listening to Steve, I think this is kind of interesting, and maybe his ride is one that we just start at the beginning with cognitive technology. So he actually shows how he started out with an incredible amount of uncertainty, with an incredible amount of change that was required for this technology to be adopted. And I think we're probably at the stage with cognitive technology today where Steve was in the early to mid-70s. So I think what I'm trying to do here is give you a little bit of an idea of at least what we're seeing, what the ride could be. Okay, so you know why is cognitive technology interesting for the consumer electronics? What we're seeing is that the Internet of Things, where electronic devices, and in fact the consumer devices probably first, are getting connected to the internet, there's sort of a couple of stages. The first stage, the manufacturers just want to optimize the business, and business case is pretty clear. This stuff is going on today, no problem. The second stage is where you actually focus to try to give the user a better experience. That is where we're actually moving from the device itself to how does it fit into people's lives. The next thing, and this is where the connectivity comes in, actually we start building ecosystems. So the first inklings of ecosystems are out there. For instance, if you look at, let's say, Comcast Xfinity Home, or if you look at AT&T Digital Life, or if you go to the Home Depot and you can find yourself, you know, a hub where you can hook things up. But that also sort of indicates a little bit of the, let's say, maturity, or let's say the beginning of the maturity that is the journey that we still have. But what we're seeing now, and that's the fourth stage, that's the stage where I think we are cognitive. This is something that I've observed now in conversations with a lot of customers over the last several days. That is, I was actually starting Wednesday morning until yesterday for just back-to-back talking to customers. And so you see, for instance, appliance makers say, okay, it's not about the refrigerator, or it's not about the oven. It is about making healthy food. It's about reducing the food waste. It is about, you know, getting it right the first time, not burning that steak. And so what's happening here is that we're not focusing the consumer devices, you're not focusing on the devices themselves, but you look at the life situations that you're trying to address. You're looking at actually the entire context. And so this is where cognitive technology, I think, will make a huge difference. So one of the things that's feeding it is the amount of data. I'm sure all of you have seen this curve somewhere. There is an absolute explosion. And if you look at it, obviously images and multimedia, so I guess to some degree thanks to Steve. but also sensors and devices. That is, for instance, we know today that even simple devices such as printers have something like 120 sensors built in. So the amount of sensors that these devices have is gigantic, but we also know that less than 95% of, less than 5% of the sensor data is actually being evaluated, is actually being put to use. And so there's an incredible amount of potential use that we can get out of that. The other part, the next part is about context. The example here that we're looking at is about health data. That is, the data that we believe has ultimately impact on health outcomes. The majority of that is actually context, is exogenous. That is, even if you add all of the genomics data about people as part of the health record, the real data, the data that actually has impact, is actually, the majority is the environment, it's their jobs, it's what they eat, where they live, how they commute, how much they sleep. That is a lot of things about the context. So if you want to make progress in this space, if you want to make progress using those data, we actually have to deal with the context. Well, how do we find out about the context? Again, it's using consumer electronics, it's using those sensors, selecting the right sensors, and then actually make sense about it. Now, once we have this much data, we're sort of running not just in the problem that, for instance, we have a little bit of trouble with Moore's law because, physics gets in the way. But now we also have a little bit of trouble because there aren't enough smart programmers who actually can code it all, can deal with all of the data, can deal with all of the complexity. And so we believe that there is a change from programming where actually people do not have to program, but actually where you program the substrate, then that learns itself. And so what we have here and what we believe, and there is some beginnings, again, we're at the beginning of the journey, where you come from the programmable systems era to the cognitive systems era, where actually systems are self-learning, they're self-adapting, where there is much of the programming, much of the adaptation actually will be done by the system itself. And we have seen some beginnings of that, and I think I'll be able to show you some examples of that, but it's an extremely exciting space to be in. So what does cognitive mean? So when you don't know, you go back to the dictionary. Cognitive says about thinking, understanding, learning, and remembering. And so this is obviously at the core of human abilities. And what we're trying to do is map a lot of those capabilities onto computing. Okay, so this looks at it a little bit in the human perspective. So you have things, and the example that I use here is a car, but you could use any kind of thing. You could use a refrigerator, or you could use a health device. Let's say a blood pressure monitor or whatever else. But understanding that thing on its own is not going to work. It has to. You have to really understand the context as well. So there is the traffic, there are the other cars, there is the cities, there is the pedestrians, there is where you want to go, there may be the weather. So there's an incredible amount of context that we have to understand if we really want to, for instance, ultimately come up with self-driving cars. That is, it's not just what you build in the car, it is how that car goes into its environment, but out of that also then comes the complexity that we need to conquer. And so we have this cycle, you sense. That is, you acquire the data, not just about the objects that are the specific focus, but also about the environment. And here already, you actually have to be smart. What matters, what doesn't, because what we saw in that curve earlier, there is an incredible amount of information out there, and simply deciding what you need is actually already a pretty difficult job. But then you have to understand, and this is where then we take the sensor data and actually lift it up to semantic understanding. I'm going to give a couple of examples later, but I mean, the point is, for instance, if somebody has, let's say, is in the kitchen and you take a cluster of readings, okay, you open and close the refrigerator, you open and close certain cabinets, you turn the sink on, maybe you turn the stovetop on. If certain things like that happen, actually it has to do with nutrition. So somebody cooks, somebody takes care of their nutrition. And so in this case, the understanding actually means, okay, how does this relate to that person's life? So it is lifting the actual sensor readings up into a semantic understanding of what does it really mean. The next step that we do then is reason. So again, if we go for the nutrition example, say, okay, I know the calorie content that somebody removed from the refrigerator. Also happens, I have access, and again, this is a totally different piece of context, happens, I know the person's health record. They might actually say, Martin, I know you didn't exercise as much today, and this is a little bit too much, so, just cool it on the carbohydrates. That is, you actually start reasoning, but that reasoning actually, again, has to happen at the semantic level. It's not that, you just write a simple program. You have to understand what it actually means in the context, and then based on that, you can actually then come to actions. And if you run through that cycle often enough, you learn. That is, that's why learning is actually in the center of that cycle. I didn't want to make the picture too complicated, but actually I might have put in the center also remember, because after the memory that is actually the history, what we're learning here is also very, very important. And so cognitive is kind of a buzzword, and a lot of people are throwing it around these days. And so how are we going to explain this in a way that is simple? It's easy. It's URL. Understand, reason, learn. And so understand actually means lifting things into the semantic level, reason, use semantic models, and then learn, that is, act, evaluate, go around that circle. Okay, so this is here starts out with, I think, what we as humans have been doing, at least most of us, and maybe most of the time, been doing pretty well. Okay, now what we're trying to do is actually make machines do that, make computers do that. And so that's the green part of the circle. So again, we sense, and here then, we have to learn which signals to pick up. We have to understand, we have to lift things up to the semantic level. Then, actually, a hard part here is the model. That is, using semantic models is really actually a pretty difficult thing to do. We're not really very well advanced in that space. But I think it's going to be important. That is, using those models, we can reason, we can put up hypotheses, we can learn, okay, and then out of that come the actions. And sometimes, the machines actually can go around that cycle a heck of a lot faster than people can. And so some of the adaptations, are pretty quick sometimes. I had a rental car, some time ago that actually used a digital camera to pick up the speed limits, and then it adjusted the speed. And I sort of looked at it when I passed it. It was less than a second before it showed me the actual speed in the heads-up display. But then sort of adjusting it, acting it, okay, you don't necessarily want to get too many tickets. This is sort of, and sometimes the cycle goes very fast. In other cases, and I'm going to show that later, I'm going to have an example, the cycle is a little bit slower. But anyway, so we believe that there is reasoning and there is acting, and we believe that this is a cycle that we're starting to execute. Now here on that cycle, I've got a couple of challenges. That is, those are the problems that we as scientists and engineers will actually have to address, will have to solve. So if we start on the bottom of the left, the first thing is we have to select the relevant sources, but also we have to verify and curate the data. That is, not all of the sensor data are right, so actually does it make sense well, when you've got into a weird outlier and a data point, humans are pretty easy to say, okay, look, this is just way out, it makes no sense. But how do you teach a machine when something is a real accident versus a false one? So curating the data is already a problem that I think we've made some progress on it, but there is still something left. And then raise the data to semantic level, that is, interpret actually what it really means, and then integrate the data into the context. Doing semantic models. Now, another aspect of cognitive computing is that we interact with the people, and in this case, the more of the action we leave to the machine, the more the humans will actually have to monitor. That is, we still need to pay attention, but what I think we need to do here is make sure that the interaction can be natural, can use human senses. I'm sure all of you have seen there are a lot of examples where people have speech control of devices. There is haptic control that's starting. There may actually be sensing as well. So I think we're making progress, but again, the cognitive interface where you understand what it means, also in terms of the language, in terms of the vocabulary, where the humans do not have to adapt to the machines, but where the machines adapt to the humans. That is part of the natural interaction. We need to make sure then, as part of that, we set the objectives right. That is, if we have the machines as agents, obviously we need to be able to make sure that they know exactly what they're doing. And all of us, or I think most of us who've written programs at some point, know if you don't get the specs right, you may actually code something, but if you forgot to tell them something, can be pretty disastrous. So if you give more autonomy to those machines, actually being able to set the objectives in a way that is safe, and for the machines then to be, let's say, cautious in interpreting those is going to be an important point. Then the reasoning itself, reason with a purpose in the semantic domain, typically developing hypotheses, but also discover new insights. That is, there is also the ability actually to do creativity, and I'm going to give you a little bit of an example. I think we have sort of like a little inkling of that. Learn at scale and speed. That is, in many ways, one of the things that our computers are typically good at is sort of munching through incredibly large amounts of data. That is, all of that stuff that's on the that's on the right side of that graph, there is absolutely no chance for humans to really do that. And also in terms of speed, so things that require speed and scale, this is actually something where computers have a great advantage, and where if we do it right, we can actually get benefits beyond what we could imagine today. And finally, going from insight to action. And so this is while a lot of these devices act autonomously, and I just saw an article today that some cars actually have been cleared for totally autonomous driving in certain states. Obviously, you have to be very careful, but also, again, you have to understand the objectives, because if you just, for instance, give, let's say, a geographic coordinate, but really what you mean, okay, I want to send something to Rick. Well, as it happens, if I found out that Rick is no longer in the office but is home, then giving the coordinates of the office is kind of not really where you want to go. And so this means you have to understand, again, the semantics as opposed to, just do brute force. So some of the things that we've started at, or some of the sort of guidelines, are actually looking at the human brain. And some of you might have heard we've started a project that's called the Synapse Project, the Synapse processor, where I'm going to talk a little bit about, and sort of look at biological simulation. So the Synapse Project actually turns out it's a very capable chip that requires not a lot of power, whereas if you do brain simulation brute force with a von Neumann architecture, that's gigantic scalable processing. There's the Human Brain Project, and then human cognition. Perceive, predict, perform. This is again going around the cycle. So the Synapse project is project where we're looking at going away from the von Neumann architecture, where now you've got a dedicated processor, a dedicated memory, dedicated storage, and so where the individual capabilities are all very concentrated, but to spread them out just like our brains work, and so to create these things that we call tileable blocks. And so we've mapped that on a chip. That chip, again, it's not designed to do things such as, figuring out how much money you should have in your bank account. That is not so much the traditional stuff that some of us used to do with punch cards, but rather these cognitive algorithms. So this is actually set out to do neural algorithms. And so what you look at here is actually this chip. Essentially, it has 4 billion transistors, but to do with comparable processors, it uses a heck of a lot less power. It uses only 50 milliwatts. And so that has sort of a couple of interesting consequences. As we know, processor architecture, sort of power is becoming more important from two aspects. If you actually want to have a lot of computing power, getting the energy back out, getting the cooling back out, and making sure your chips don't fry, is in the high performance processing a big deal. But on the other end of the spectrum, as people have these wearable devices, when you don't have a lot of battery, actually having devices that take very little power is going to be important as well. So what you see here is actually an output of the Synapse chip. So this thing learns, and you see it in this thing. This is, by the way, this is real time. This is not a speeded up simulation. In this chip, it learns to identify people, things going on two wheels, and cars. And so this is not necessarily a very recent thing. I think we did this a couple of years ago. But this shows how, if we get the right kind of architecture, we can actually make a big difference. As I said, this is fairly specialized. This is for neural networks. Maybe other processors need a different kind of an architecture. But for us as a community to rethink that, looking at where we want to take it, is going to be important. This is sort of another piece of experience. Sometimes learning is not really fast. What you see here is the history of how our team, and I can't take any credit for it myself, I was not part of that team, got to winning the Jeopardy game. So on the vertical axis is the precision, that is how many answers are correct. And on the horizontal axis is how many questions did the machine actually attempt to answer. And the bottom line happened in December 2006, and the top line happened in November 2010. So it took a while, and what happened actually going up there is essentially, once we had that line, by the way, the red dots are all the data from the world champions against whom the Jeopardy played in that contest. So once we had that blue line, we figured, okay, if we have a good day, we're actually going to get there. But the way we got up there was essentially painstaking training the machine. Now, how did the machine look? So this is the pipeline that the machine actually took. It took the question, then it analyzed the category of the clues, then it did some primary search on a database. Actually, we had the database at the bottom was all in real memory. It was, I think, I'm not 100% sure, so don't quote me on that, but it was, I think, 150 gigabytes of RAM, something outrageously big at the time. The primary search, and then it actually did shallow scoring and created hypotheses. Then it went back to the database to look at supporting evidence. then it scored the evidence, and it actually came up with a ranking, used some statistical model, and answered. And all of that has to happen within less than 3 seconds. That is, none of the answers were actually, didn't make, or if you compete there, if you take longer than 3 seconds, you already lost even if you got it right. So now the other aspect of this is, it wasn't a single model. It was actually a large group, a large of configuration of individual models of analytical modules. So for instance, when it sensed at the beginning that, there is something about geography, then it kicked in the geographic algorithm. Well, there is something about time, then it kicked in the time algorithms. That is, there is actually a dynamic configuration of algorithms as you go through, simply based on what the question was. So I said, it's sort of fairly specific, but part of the objective of the game was, as you probably can understand, IBM is not in the business of doing game shows. Part of this was, can we show that computers can have semantic understanding of language? And once we look at this as a goal, then the question is, what is sort of the proof point? What are we going to use to show how we got there? So obviously what we did since, actually, we started initially to apply the technology to medical research. That is, there's a lot of work in oncology going on. But we're opening it up now, and so we've got a lot more experience, a lot more skill, and we also have a lot of collaborations with academic groups, simply to enhance this. But language understanding is one of the key skills, one of the key things that we need to understand for cognitive computing. Another sort of aspect here is how do we configure these things? And so what we've got in what we call the cognitive experience room is a whole bunch of individual cognitive agents that communicate among themselves. So there is actually, you can see obviously human to human plays a big role, but cog in this case, that's I guess a cute name for cognitive agent, cog to human. But then we have things such as personal avatars, we've got object identification, sensitivity analysis. There's a lot of algorithms that have to kick in. And one of the things, for instance, that we're doing with this thing right now, I don't know, some of you, if you have visited us, might have seen this, is we're applying this, in this case, not so much for Internet of Things, but to actually do evaluate options in mergers and acquisitions, sort of getting all kinds of data, from all kinds of sources. Another point is, if we want to get into actions, if we want to act, big data is sort of a big buzzword, but big data that mostly works and relies on the law of large numbers, in many cases cannot be used when you actually have actions. Because the context, an action typically is in a specific situation for a specific purpose with targeting a specific outcome. And so in many cases there isn't sufficient data to actually provide very high confidence for the results. So obviously one way to do is that we have to be careful, but another aspect of it is to establish the semantic context and to get a little bit better on this. To give you one example, it almost seems like it's a law that in the security industry, 90% of all the alarms are false. Well, if you only look at one sensor, yeah, it's possible. But we already know that if we then bring in the context, let's say you've got a warehouse or let's say a store, you say, okay, should the store be open, should it be closed, which employees should be there, should it be lit up, what is the schedule? That is, if you have a lot of the context, you can actually reduce that substantially. So the context, bringing context in actually will increase the confidence. Using semantic models is going to be important, but also then acting strategically with caution. That is, this is where we have to essentially make sure that we're going to do it fail-safe. And then feedback and adapt quickly. because the self-learning actually sort of makes a big difference. That is, going up that curve for jeopardy that you saw a little bit earlier, that was actually through learning. That is, moving from one stage to another did not really tell the system, okay, this should have been the answer, but simply you were right and you were wrong, and this is a better source, such that the system was self-adapting, such that it learned, okay, which are the more reliable sources, in what situation can I apply what algorithms, so that the system configured itself. So again, this stays in the lower. If we do this right, and if we have the right kind of capability, we can stay in the lower part, in the green part of that circle, rather than having a lot of human adjustment. So here's one of the things that we did is, you see on the left, the floor plan of an apartment, and you see all of these little sticks that represent sensors. And so what we've looked at, can we characterize activities of daily living? And so the case that we're looking at here is, okay, what does it mean that somebody cooks? There are more, but the clusters here, there are 3 clusters of events, 3 clusters of sensor events. One of them is the microwave, the cabinet, the fridge. The other, toaster, pantry, cabinet, and the fridge. And then the other is the the stove, the cabinet, and the fridge. And on the right side on top, you see a bunch of algorithms that we tried out. And as it happens, k-means and a priori had actually the lowest number of false positives and the lowest numbers of false negatives looking at these things. But again, we're at the beginning. I'm not exactly sure yet where this is going to end. But and I'm also not sure whether I in my apartment would 100% want to rely on this yet. But I think this is one of the things to come. And as we saw, the way Steve showed, how actually things can be amazingly progressing within 30 years. I think we've got a great future here. Finally, I want to show you something here. It's not just about understanding, but here is something where we actually tried to see, can actually computers have creativity? That is, it's not just cognitive. It's not just recognizing and acting autonomously, but also can we be creative about it? And so some of you might have heard about Chef Watson. If you have not, there is this URL up top that says ibmchefwatson.com. This is actually a free URL. You can go there and try it out. So what you do there is, I said, okay, I want to select some ingredients. What you see here, I said, I want to have artichokes, beef skirt, I want to have ginger, and I want to have leeks. And it wasn't looking up a recipe, but rather it created a recipe based on something that may be a recipe that was close, but also it used things understanding what happens when you cook, that is the cooking processes, what tastes go together. And so it does that. We sort of introduced it a couple of years at South by Southwest with food truck, but now this is actually publicly available. So you see here, it came up with artichoke hearts taco, and to show then how this relates to consumer electronics, we're actually now in discussions. How can we take this and link it directly to ranges? That is, we're talking to a couple of appliance manufacturers, and the problems that they have is they've put more function into those devices. The complexity, the operating complexity explodes. It gets a lot more complicated. For instance, one fancy thing that is probably more popular in Europe than here in the US, it is steam cookers. Now, if you do a steam cooker, it's not just you set a temperature and let it go for a certain amount of time. It's actually, it goes at this temperature with this steam density for a certain while. Then you add other food, and then you change the density. Then you add this. That is, it actually, cooking becomes a program. Okay, now, what cook wants to be a programmer? I think probably not a lot of them. And so what we could actually do is translate the recipe that comes out of that directly into the instructions for the oven. And then it would say, okay, now add this, now add this, now add this. And at that point, actually, it becomes really simple. So here is sort of an image of the data that are actually being used to understand this. So I don't know how good the resolution is, but the different colors actually mean different categories of fruit. So food. So there is food, dairy, spices, meat, seafood, etc. So each of those colors represents a different kind of a food class, and then the the size of the circles are the prevalence, and then the lines are shared components and the connectivity, how they actually go together or not. Again, this is something that the system learns over time, and the way this Chef Watson thing works actually started out, we started feeding it with about 9,000, actually no, I didn't want to go there yet. Can I go back? Yeah. It started out with about 9,000 recipes from Bon Appetit, but every time somebody creates an additional recipe, it actually gets added to the corpus, and also it gets to the point where it says, okay, I like it or I don't like it. That is actually, again, the feedback. This is good or this is bad. So it's actually, this is an ongoing learning system. There is the general broad-based, but it is also personalized. That is, for instance, my younger son actually has nut allergies, so we could set this that when he's home, no recipe will be proposed that will have nuts in it, and the system actually will be able to do that. So those are some of the things that are looking at, acting, but even getting to the point of creativity. And it looks like we have a little bit more time, so I want to show you a couple of projects that are sort of, again, at the beginning of the journey. So in this case, we use a robot. This is actually a humanoid robot, and as a sales consultant. So in this case, the example is that you go into a store, and then it actually approaches customers and says, okay, what would you like to buy? I'm not saying here that this is going to be the future of retail. I'm not in the retail business. Again, we used this simply to say, okay, is this actually, could we do a reasonable dialogue? So this is actually simply understanding what the system can do and what it can do. As I said, it's not, I'm not predicting any, what happens in retail. And so let me see. Anyway, so what you see here is actually sort of, again, in this very simple case, you have a relatively large number of steps that the robot actually has to understand. So you find the customer, approach them, estimate that is he happy, is he not happy, that there is actually some emotional issues as well. One of the hardest things is actually a dialogue. That is, the Jeopardy system did question and answer, but actually going then from one answer to the next question is actually a very complex process. So this is one of the difficult processes. Here is another project, and again, I'm going to go through this now, not touching the videos, and then play some of the videos in a little bit. We're working with an intelligent home, so there's a couple of things that we're doing there, but the one thing that I wanted to show is how it actually helps people with their nutrition. So there's a video camera that actually sort of records and analyzes what people eat. And so the situation that you will see is there's a person who says, okay, here's what I would like to have for dinner. And then the system comes back, says, this is what you had for breakfast, this is what you had for lunch, okay, so then let's see about it. And I think the video is probably the best way to show that, so I don't want to get more into detail here. The picture that I showed you a little bit earlier about the apartment that where we sort of figured out, where the people were actually taking care of the nutrition, was part of a bigger project. We worked with a business partner to determine what could we do to help people for aging in place, that is, older people. As you might know, this is an increasingly difficult problem, probably even more so in some Asian countries such as Japan and China than it is here. and is there actually something that we could potentially do to help? And so there was a very, very rich instrumentation, and we looked at what could we do. And so in terms of the technology, you actually see here fusing the data from a lot of sensors, doing personalized spatiotemporal activity signature for each of these activities, and then that is identifying the sensor cluster for those activities. Customizing the APIs, I guess we did okay on the synthetic data. On the real data, there's quite a bit of improvement left, to be done. And finally, this is the last project I want to talk about, but I'm also not going to touch the video on this one, is we're working with the city in Beijing on a project that's called Green Horizon. If you guys have sort of watched the news recently, you probably saw that pollution in Beijing and in a lot of other places is a fairly serious problem. And so if you look at it here, we've got an incredibly large number of data sources on the left. We've got a lot of other data, historical data, and other things on the right. We fuse all of this together, and by doing this, we've actually learned now to start predicting air pollution. We have not figured out yet to do the ACT piece, that is where we actually can try to reduce it, because obviously, as you understand, the context in this space is pretty substantial. But the point is that we actually can start looking at really big problems this way. This is it, in this case, it processes something like 34 exabytes every day. So from a scaling perspective, this is a pretty interesting problem. Okay, so let me now go into the file system, because I think that's a way to really show the show some of the videos. The fact that there is no sound actually is not a problem, because at least for most of us, including myself, it's Japanese. Actually, we taught Watson Japanese, and so this is part of the program. So we did this with a business partner. So all of the important information is actually the subtitles. So you see here how they monitor. There is a sort of a relatively large building in Tokyo where we have this deployed, and so you can actually see here where they follow this person through the building. And then so, okay, at least indoor you did not really have a lot of activity. But this is the interesting part here. So he says, okay, what are we gonna have for dinner? So it shows you here breakfast and lunch, including things such as how many calories, what is the nutritional content. And so he puts his food here, what he wants, what he wants to have. It says, okay, evaluate it. And now if you see that, let me just stop it here. You see actually here is, 2,400 calories just for dinner is actually quite a bit, but it essentially evaluates the whole thing, initially simply based on a visual analysis, but I think as we move along, using things such as spectral analysis, we probably can get even more detailed. There is sensor development that will help. And so here, this is actually a detailed evaluation of what the guy is eating. Okay, sorry. But also now you see there's a slightly more elaborate evaluation. Okay, so his fat needs to reduce the fat, get more calcium. And he can actually ask now, and you can see by pointing to it, he can actually then ask more about the details of each of the dishes. Now maybe the interface of that is all a little bit awkward yet. But I think, it's too obtrusive, and it's not clear that people will accept it. But I think the capability that it shows, if we do it right, is actually substantial. Okay, now let's do one more. So this is the robot as sort of a sales consultant in a store. And again, it's not that we're saying that this is the way it's going to happen in the future, but rather this was simply a way for us to test how far we have come. And again, the audio is actually Japanese because, again, this is part of our Japanese language program. Okay, so let me stop here with the presentation. Let me just sort of give one final example that I was not able to show you because it actually got released only on Wednesday when Ginny Rometty, our CEO, was giving her keynote. And this is, we are now able in a collaboration with Medtronic to detect diabetic shock 3 hours before it actually occurs. Nobody has managed ever to do something like this before. Again, this is like a single advance, but it is an advance that, at least for certain people, is life-changing. And I think this is what we can expect to get more of if we really apply ourselves. And so let me stop here. I'm going to be around if people have questions, or if you want to do some questions right now. Whatever is the preferred way.
Well, we're running a little bit over, but it's by design. And if somebody has a quick question or comment, I think we should allow that. As long as we don't have a cognitive replacement for an engineer yet, I think we're not worried. But maybe that's coming down the road. One quick question, please.
So yeah, it's really fascinating, amazing engineering feat. But one thing, I mean, it's something, I understand when it solves major problems, you said, or like, the medical arena, or figures out predicting the pollution or something. But what about, when you talk about things like this, or the food thing, I wonder, does it kind of induce a de-evolution, kind of in a way? I mean, it took us millions of years to figure out how to walk, right? But it only took 10 years with smartphones to forget how to walk and to look down and run into stuff while we're walking, right? I mean, so with too much dependency, like you said, with the food, with cooking, are people going to forget how to cook? And do we put too much in the hands of things and kind of de-evolve in a way?
Some of this may happen, but if you step back, for instance, what are actually the activities that you really want to do, and what is sort of just like the operational context? When I learned driving, the transmission was manual and it wasn't synchronized. That is, I had to double clutch when I was downshifting. It's hard to get a manual shift even here in the US. Okay, so you focus where you want to go. And what I think this technology, if we use it right, it will actually free us from the mechanics. It will free us from the operational stuff that in many cases takes a lot of skill, but isn't really very productive. That is, let's say the mechanics of cooking, but actually with respect to particularly your cooking, this is sort of an interesting question. One of the design engineers of a major appliance manufacturer said, got to be careful, and I think he goes in exactly the direction that you went. This is not to essentially take the joy of cooking away. That is, when I come home, had a long day, it may actually give me something quickly. But if I have time over the weekend, it may actually give me new ideas, things that I have never cooked before. So part of the objective, and in this particular case, that company is working very hard on this, is to increase the joy of cooking, to increase actually, to help people to accomplish the results. One of their mottos is, get it right the first time. That is, never burn anything. So it allows then more exploration. Ultimately, it's up to us, because one of the things that I'm seeing here, and this is sort of, I guess, part of the other part of my job that I didn't talk about here, is how fast is this going to get into the marketplace? What is the business model, et cetera, et cetera. What we see today is incredible possibilities, but the majority of them will go to market only if there is sort of mass interest. That is, if people actually want it. And so it is up to us to decide, is this going to make my life easier, more productive, more enjoyable? And as I said, you know, there are certain aspects about cooking that I wouldn't be able to do myself. But there's other, so if it takes care of some of the operational things, if it takes care of some of the complexity, it's a good thing. But in other cases, if we do this right, it actually helps us to explore, which is why we started to think about the creativity part. That is what the Chef Watson part. Again, IBM is not in the cooking business, but when we asked our engineers, okay, what are, you know, do you have any good ideas about trying out whether we can be creative? That was the most interesting one that people proposed, and we said, go for it.
Well, thank you. Rick, it's over to you.
Okay, thanks.
Martin, on behalf of a very grateful IEEE and ICCE, we'd like to present you this keynote plaque to you. Okay.
Thanks, Rick. Thanks.
Thank you.
Yeah.